name is Tim Becker, and I'm a researcher at ChainLight. And today I'm going to talk about Relic protocol and how you can build on-chain applications that access historical state from both L1 and L2. And because that's not a very creative talk title, we had an LLM come up with our actual title, which I think turned out pretty well. So we'll start with the fundamental problem that we're trying to address here, which is that on-chain data access is very limited. So from smart contracts, you can basically access a subset of the current state of the chain. So this includes all of the account balances, your contract storage mappings, and of course you can call other contracts and get results from their functions, but you cannot directly access the state mappings of other contracts. And some will say that this is for a good reason, like data encapsulation and all of that stuff. But I would argue that more often than not, this is not for a good reason. Either it's an oversight of the contract developer, where they didn't see a use case for this, exposing this data, or it could be to reduce the size of the contract so that it fits under the code size limit of Ethereum or whatnot. Another huge set of data which you cannot access are log emissions. So off-chain, we take this completely for granted. Most indexers off-chain rely basically entirely on log emissions. But from smart contracts, you actually have no way to access this set of data. And so if some on-chain interaction happened that only emitted a log, or maybe the most convenient data format was in a log, there's no way for you to access this on-chain. More generally, you can't access historical state of any kind. So even if something was in storage, even if it was in your own contract storage, but 5 blocks ago, there's no good way to access that. So this is kind of the problem we're trying to solve. And just as a simple motivating example, we can say, what if your contract wanted to know who owned this pudgy penguin at block 15 million? So this is a very simple question you can ask an RPC provider like Infura or Alchemy. And of course, you can also query any archive node, and they'll be able to answer this question for you very easily. But if you were to pick a random node on the Ethereum network, you would instead get this horrible error message about some missing try node, and it will completely fail to answer this question. And the reason for that is that on Ethereum, old data is pruned away for most nodes. It's only required that nodes keep the current state of the chain. And so once the data gets old enough and is finalized, most nodes will prune it away to reduce disk space and make it easier to run nodes. But if you look at how this data is actually stored, so basically everything of interest is either in the block header or in a Merkle-Patricia trie, which is committed to by the block header. And this includes all of the account balances, all of the storage, transactions, logs, everything. And because it's in this Merkle-Patricia trie, which is kind of like a Merkle tree, you can generate very short proofs of any data in the tree that you want relative to the size of the tree. So even if there's hundreds of millions of Ethereum accounts, it only takes like a few kilobytes of data to prove information about any one of them. You can actually ask any archive node and most RPC providers to generate you these proofs. And here, for instance, we're asking who owned that pudgy penguin, and it'll give you all the data you need to verify that at that block, this was the owner of that pudgy penguin. And so what does verifying these proofs look like? It's actually just dominated by computing a few Keccak hashes, which is really not very expensive. And in fact, it's completely cheap enough to do on-chain. So depending on what kind of data you want to access, the cost will range from, on the low end, like the equivalent of an ERC20 transfer. And on the high end, it'll be maybe more like a DEX swap. But these are completely reasonable gas costs that, for some applications, make perfect sense to do on L1. And of course, if you're on L2, these gas costs make even more sense. And we'll get to some more stuff about L2 shortly. So this actually glosses over one small issue, which is that from your smart contracts, you don't actually have a way to get all of the historical block hashes. So the EVM only gives you direct access to the last 256 block hashes. And if you want older ones, of course, you can verify them by unrolling the blockchain, by providing all of the intermediate headers from when you can verify back to what you need. But of course, this is way too expensive to do on-chain and even off-chain, honestly, because the cost is linear in the age of the block. So if you want 1 million blocks ago, you have to compute 1 million block hashes, basically. So there's a better way to solve this problem, which is to basically do this unrolling of the chain only one time and do it in a zkSNARK. So what you can do is you can take a sequence of consecutive block headers, and in a zkSNARK, you can compute all of their block hashes and verify that they are correctly linked to one another by looking at the parent hash field. And then you take all of these block hashes and you build a Merkle tree of them. And what you put on chain is only this Merkle root and the proof that all of this is valid. And then by caching this Merkle root on chain, you can quickly verify any historical block hash by simply doing a short Merkle proof of all the block hashes. You don't need to do the whole unrolling and link verification anymore. So yeah, just to really emphasize this point, this is a one-time cost that you do upfront at the start, and then you're able to access historical block hashes very cheaply on-chain. So then what about L2s? So there's actually two questions here. One is reading L1 data from L2 contracts. And this is actually very easy because L2s are able to trustlessly read L1 data, at least most of them. And so we can use exactly the same scheme and give L2 contracts access to all of the historical L1 data. And this makes it extremely cheap to do basically any sort of use case, which we'll get to in a moment. The other question is, what about L2 contracts accessing historical L2 data? And this is a little bit harder because the block times on L2s are a lot shorter. And so the sort of the costs of doing that zk verification are proportionally higher. But new zk proof systems may make this completely feasible in the near future. But I also want to highlight another partial solution, which is we can use the ability to trustlessly read L1 data to actually read the state roots of the L2s that get posted there on the L1 and use those to access L2 data. So this is basically like a near zero cost solution to get L2 contracts to access historical L2 data. So yeah, I mean, this kind of solves the problem of historical data access on L1 and L2. And this is basically the scheme we've implemented for Relic protocol, which is on-chain protocol for accessing all of this historical state. We have SDKs for proof generation, which are JavaScript and TypeScript, and verification, which are Solidity. And so it kind of abstracts away all of this logic about the proof verification and generation that's somewhat complicated. So developers can just focus on the use cases for this data, don't need to worry too much about what's going on behind the scenes. Relic is built with immutable modular contracts. So we thought really hard about forward compatibility and how to minimize trust. So I'll talk about that more in a moment, but there's not really many trust assumptions being introduced here. And yeah, so we've been on L1 for a year and a half or so, and we recently deployed on L2s, including zkSync Era, Optimism, and Base. And the Optimism Base support is basically Optimism Bedrock support, so any chain that builds on that platform will be able to support very easily. So you may wonder, why isn't this just a library? Why do we actually need a protocol? Why do we need common contracts? And there's two main reasons for this. The first one is forward compatibility. So because getting at this historical data requires digging into the internals of Ethereum, there's always the possibility of breaking changes happening. So one major one are Merkle trees. If those are implemented in the future, that'll swap out the Merkle-Patricia tries for a completely different scheme. And so the way that you verify data is going to have to change. Another thing is new features and new optimizations. So EIP 4788 is coming in the Denkun hard fork. And this gives the execution layer access to the beacon state root. And so using this, you can access all of the beacon data as well. But also, this actually unlocks a cool optimization for accessing execution layer data as well. And this is kind of out of scope of this talk, so I won't get into the details. But the fact that Ethereum protocol updates and there's breaking changes or new features means it's nice to have a convenient one location where you do these upgrades. Yeah, but I want to emphasize that any projects that use Relic are completely in control of which versions of these verifiers they want to trust. So there's no forcing any updates or anything like that. Yeah, the other major reason why this isn't just a library is cost amortization. So this one-time cost of doing all the zk proving and any sort of intermediate proof data that multiple people want to access can be cached. And so the costs of proving all of these things can be amortized across everyone who uses it. And so this basically just makes it cheaper for everyone who wants to access historical data. So I want to highlight a couple of use cases that we envision for this. One kind of obvious one are airdrops. So most airdrops, as you know, are based on on-chain activity. And usually the way it works is the project organizers will sort of index all of the stuff that happened on chain, determine who is eligible for the airdrop, Merkleize all of those claims, and put them on chain for people to claim. And in many cases, this is just a very simple transformation. And so it's trivial to just instead write this as a system that uses Relic to basically on-chain directly verify that the user performs some on-chain action and is therefore eligible for the airdrop. Yeah, another huge category is governance. So because we have the ability to access data at some fixed block in the past, we basically get free on-chain snapshot voting. So it's somewhat expensive to do on-chain voting, but because we have the ability to do this on L2 and reference L1 data, you can actually do all of the voting on a cheap L2, do all of the vote aggregation, determine the result, and trustlessly send that back to L1 for your proposal to be executed. So yeah, instead of being dollars per vote, it's pennies per vote. And it makes on-chain governance very practical. Another really cool use case are voting pools. So I want to shout out Federation here, which was one of the first projects that built on Relic. It's a Nouns DAO ecosystem project. And what they did was build a governance pool where people can delegate their Nouns votes to a smart contract. And then this voting pool was controlled programmatically. And in their case, it was actually auctioned off. And then all of the people that delegated to that pool were able to claim their portion of the winning bid, which was really cool. Another use case category is reputation and identity. So using something like Relic, you can prove any historical on-chain action and tokenize it as a soul-bound token. And then you can integrate that with any existing identity ecosystem. But you can also do feature gating or provide special perks to users that have high reputation or that can prove that they participated in some previous actions in your project. And kind of our proof of concept in this category is a on-chain birth certificate. So you can prove when your Ethereum account was created, the first block that it was created, and tokenize that as a soul-bound token, which has some cool on-chain generative art that we did. And yeah, the final category I want to highlight are oracles. So using this, you can build a trustless oracle for anything that's on-chain. So even if a project didn't intend for their price feeds to be an oracle, they didn't integrate a TWAP or something like that, you can use this to get at that data and produce an oracle from it. And this is completely trustless, so it doesn't rely on anyone relaying prices. And another really cool thing is that because you can read L1 data on L2, you can bring any oracle that's on L1 and access it from L2. So that oracle doesn't need to explicitly support that L2. You can just, as soon as the price update's posted on the L1, you can instantly access it on the L2, and you just kind of inherit all of the oracles from L1. So yeah, those are just a few examples. If anyone has ideas for other cool things you can do with this, we'd love to help and support your project. You can find our docs here, join our Discord, follow us on Twitter. Yeah, be happy to take any questions if there are some.